All right, 10.3, we're going to review or sort of make a synopsis of all of the different things we've done with our activities over the past few days. So we're going to look at powers and roots of complex numbers with the big goal here of looking at De Moivre's theorem and how we can use it for applications of taking powers of complex numbers as well as roots of complex numbers. And then Euler's formula, which is that e to the I theta for translating between notations for complex numbers. We're also going to do a few applications there. Okay. So from our previous in-class activities, we have discovered that De Moivre's theorem says that if I have z to the nth, which is cis theta to the nth, then r, extra brackets around there, that is equal to r to the nth times cis of n times theta. And if you look back from your notes the other day, our big idea or reflection is that if I have some little complex number like that, and that I take a theta and I multiply it by itself, let's say I'm going to take it to the third, that it's going to scale and so there's 1, 2, 3, and it's going to be that big. So it's going to be scaled by its r. So if this were 2, then this would be 2, 4, 8 long. And let's say this is 30, then it goes 30, 60, 90. So example 2 cis 30 to the third is 8 cis 90. Or pi, if you'd like to use pi. So for example, let's find z to the 10th of this term right here. And the first thing we need to do is put it into our cosine I sine notation. And right here, I went ahead and calculated r in advance for us. And then 8 plus 8i is going to give us a 45 along that trajectory. I know that because they're the same value, so it must be a 45. And then these are both positive, which puts it in this quadrant. So this is 8 root 2 cis 45, or 8 root 2 cis pi over 4. We're going to take all that to the 10th. So let's apply. And I'm going to skip over actually taking 8 root 2 to the 10th and just leave it as 8 root 2 to the 10th to make my life a little easier. If you'd like to calculate that out, you can. And then cis 45 becomes cis, and 10 rotations of 45 degrees is cis 450. Or you could do it with this notation here, which would be 8 root 2 still to the 10th, and then you'd have cis 10 pi over 4, which would reduce to 5 pi over 2. Oops, that is not focused, so we're going to refocus. Okay, I might have to close between the next two examples here. Let's do that. Give it a quick. See if that makes it better. All right, that's a little better. So here we have another one. This is 3 root 3 and negative 3i. So the first thing we have to do is calculate what r is for us. So negative 3 root 3 squared plus negative 3 squared summed and square rooted to give us the magnitudes, just a formula for distance. So that's 9 times 3 for that component, plus 9. So 27 plus 9 is 36, which gives us 6. So if we wanted to scale z down in order to find where it is on the unit circle, we would need to divide that magnitude out. So negative 3 root 3 over 6, comma, negative 3I over 6. Oh, there's our root 3 over 2, comma, 1/2 negative I, which puts us down here in the third quadrant with our x value being the longer value. So that's this guy right there, which is 30 degrees ahead of 180, 210. And I'm actually going to go ahead and close this. Sorry, guys. Let's try closing and opening it, see if it helps it stay a little bit more clear. All right, hopefully that'll make it a little better. All right, so we have cis 210 with a magnitude of 6 is equal to z. Z to the negative 7th is going to be 6 to the negative 7. Cis 210 to the negative 7th would be, oh man, I wish I had a calculator. We're just going to do it like this, times negative 7. And then you could find the coterminal value. So this right here would be 1 over 6 to the 7th, so the negative exponent, cis, scratch work, 21 times 7, 147, and then multiply by our 10. Negative. And you can leave it negative, that's fine. It just means that you're rotating the other direction. Okay, applications of Dumois theorem. This is this next page. So if this is true, and it's true for all powers, then 1 over n gives us r to the 1 over n, cis pi, or whatever our angle may be, divided by n. Okay, that makes it really easy to take roots of answers. So let's use another application of Dumois here. So roots of unity is one of these things. What unity here means 1, just kind of fancy. But we're going to look at all of the different ways we could take the square root or the cube root or the 5th root or the 8th root of 1. Okay, so let's say z is equal to 1, and let's write it in a couple different ways. 1 is going to be right there, right? So that's 1 as my magnitude. If we want to write it in, we can, which would also be written as cis 0, or maybe we write it as 1 plus 0i. And then if you're a little further along, you might say that that's e to the I 0, and anything, again, to the 0 is just 1, so it works out. All those are different ways we can look at it. So we need our answer to end here at 1. So, well, one of them we know. That's the easy one, right? 1. So x squared equals cis 0. Okay. Well, what is 1 to the 1/2? It's just 1. And then cis 0, well, what's 0 over 1/2, or 0 over 2? It's also 0. Okay, so there's one of our answers. And then we know from previous experience or from our activity the other day that our other answer is -1. Because -1 squared puts us back. So here we have a theta of pi, and pi times 2 brings us back to our end point. So each one of our complex number, when cubed or squared or taken to the 5th or whatever the case may be, which is when I do that many rotations of it, it ends where we need it to end. And where do we need it to end? At 1. So So we've got some more roots of unity here. So here's 1. Well, 1 cubed is still just 1. We're going to jump ahead to the bigger ideas from what we were looking at the other day. So we need to go 360 degrees in 3 even increments. So cis 0 when cubed equals 1. And I need to get all the way back around to 360 in 3 even jumps. That puts us here at 120. So cis 120 cubed equals cis 360, which is 1. If I do that 3 times, I end here. And the last one, which is a little bit trickier, is 240. .240 cubed is 240 times 3, which is 720, which is 2 full rotations around with the right endpoint, also 1. Okay. Let's look at the next one. These are our 3 answers, by the way, here. And these are our 2 answers here. Let's look at 5. I have to get 5 answers. The easy one for 1 is that there will always be an answer at 1. And then let's say x to the 5th. Instead of going cis 0, let's say cis 360. Which means I have to break this guy up into 1 over n, so 360 over n, or 360 over 5. Is 72. Okay, so that's just a little scratch work there. So the first answer is going to be 72 degrees. Okay. Our next answer needs to be 72 degrees further. So each one of our breaks here needs to be a turn of 72. So the next one would be at, let's say, here at 144. And the last one, well, it's not the last one, but we're going to say one more, gives us 216. It's going to be like here-ish. So we have 1, 2, 3, 4. And then we'll say the last one's like here-ish. You can calculate the last 2 answers. So 1, 2, 3. 1, 2, 3, 4, 5 answers. Right, to the 8th for the unity one is going to be evenly distributed in 8 pretty little answers. So the easy ones would be here, 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 and here, right? To break it up into even pieces. And then there is 1, 2, 3, 4 more. So there's 1, 2, 3, 4, 5, 6, 7, 8. So if x to the nth equals z, then there are n number of answers evenly distributed around the circle, or around the 360 degrees, or maybe 2 pi, doesn't matter, however you want to note those, that's radians. Then we're going to go on and look at some more kind of ugly looking ones here in a minute.